Hello students, welcome to Sourav classes. We will be solving the paper 2 chemistry and we are discussing over here the organic questions for the Combined Geochemist examination held on 2021. Question over here is the total number of delocalized pi electrons, okay, in the compounds 1 and 2. All right. The theory is over here that for every C double bond C or C triple bond C, we will count 2 pi electrons. Okay, so if we start numbering these unsaturated bonds, then we will say that this is say 1, that is 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6, 7. So for structure 1, we have over here 9 into 2 pi electrons, that is 18 pi electrons, and for structure 2 we have 7 into 2 pi electrons, 14 pi electrons. So obviously our answer over here is going to be 18 and 19, 14 respectively. So option A is the correct option. Now question number 82, it says rank the following structures in the increasing contribution to the resonance hybrid. Theory is neutral, resonating, structures contribute more to resonance hybrid than charged resonance structures. Okay, so that way obviously we will say that one will be more contributing among 2 and 3. Okay, so obviously from that only we can say that B should be our correct option over here. Now, sorry, why 2 is more contributing than 3? Then obviously we can see that here carbon is having octet configuration and here carbon is having sextet configuration. So we will say resonating structures that have all the atoms in octet configuration is more contributing than where octet configuration is not present. Okay, so that way then we will say that one should be more contributing, followed by two, and at last we will have three. And so, as I have mentioned before, okay, that the option will be over here B. Question out here in 83 is which of the following indicated atoms in each species has a sp2 hybridization? So, rule out here is lone pair oblique negative charge on atom if conjugated to a pi bond, then it will be sp2 hybridized. Okay, that is a simple thing that one needs to follow. Again, imine nitrogens are sp2 hybridized. So it can be N substituted imine or simple imines. Okay, so over here, if we consider the point B, we will say obviously C double bond N, it has to be sp2 hybridized. Okay, now what about 1, 2, and 3? In case of 1, we can see that this particular carbanion, the negative charge is delocalized with the carbonyl bond and it leads to the formation of enolate via resonance. So obviously we will say this is also sp2 hybridized. Okay. In case of the carboxylate, this negative charge is again delocalized via resonance. Okay. And we can write another canonical form for structure 2. Alright, so also we will say this is sp2 hybridized. For the benzyl, also this is sp2 hybridized. Why? Because this negative charge can be delocalized within the ring and we can subsequently write another resonance structure as I am showing over here. So again, we can see that in case of 1, 2, and 3, all the negative charge are delocalized with a pi bond, and so the atoms bearing this negative charge will be all sp2 hybridized. And for nitrogen, we have already explained that this is a imine nitrogen. Okay, that is, it is C double bond N, and so it is going to be sp2 hybridized. So our answer over here is going to be obviously D, the correct option. In the question number 84, it has been asked the total number of hyperconjugative structures possible for the carbocation is, we have to find out. So, number of hyperconjugative structures we will say is proportional to number of alpha hydrogen atoms. Okay. So as we can see over here, with respect to this particular carbon, we have this alpha carbon and it is having 3 such hydrogen atoms. So over here obviously we will say that this particular compound is going to have three hyper conjugative structures. So simply counting the number of hydrogen atoms on the carbon next to the carbon having positive charge, okay, we can predict how many hyperconjugated structures are going to be formed. And so our answer over here is going to be 3. In the question number 85, it has been asked, which one of the following statements regarding polarity of bonds is not true? Okay, the statement A, it is saying a compound with only one polar bond must be polar. Obviously, this is true. For that, we can take an example, say HF. Okay, and or let's take this one, which is say something like this. So this is a polar bond out here. All right, and so we know that this is going to be having dipole moment, and obviously this will be polar. So obviously statement A is true. In the statement B, it is saying a compound with two or more polar bonds will always be polar. No, this is not true, because if we take the example of carbon dioxide or carbon disulfide, the C double bond O dipole moments are acting opposite to each other. They will cancel out, and the resultant dipole moment of carbon dioxide is going to be 0. Similarly, for a molecule such as BF3, which is having trigonal planar shape, okay, the BF dipole moment, okay, and say the resultant dipole moment of these two BF bonds, which are lying at an angle of 120, okay, so this particular dipole moment will be lying opposite to this particular dipole moment, okay, and that will cancel each other. So we can say the mu resultant over here is going to be cancelled by the mu BF, all right, and such cancellation will again result in the total dipole moment to be as 0. Okay, so obviously we will say the statement number B over here is going to be not true. In statement C, they are saying a compound cannot be polar if it contains only non-polar bonds. Obviously, as I have explained in this example and in this example, we can see that we are having polar bonds, but if the polar bond dipole moments are cancelling each other, okay, then obviously the compound will be non-polar. Okay, so obviously statement number C is going to be true, which says a compound cannot be polar if it contains only non-polar bonds. Okay, the statement can also be justified by taking another example in which, say, suppose we have taken CCl4, that is carbon tetrachloride, all right, where we can say that the CCl dipole moment over here is acting in this direction. So say suppose this is mu CCl, okay, and this dipole moment, that dipole moment, this dipole moment, okay, if we add all these three dipole moments over here, okay, then what we will find that this resultant dipole moment, that is this mu resultant, will be exactly lying opposite to this particular dipole moment, and these two will again cancel each other, okay, and the total dipole moment for this molecule will again be equal to 0, okay. So obviously statement number C is perfectly correct. Statement number D says more electronegative atoms pull electron density towards them, making a dipole, which is true. Let's take the example of HF, wherein F is more electronegative than H, and hence it will be developing a partial negative charge. H will be developing a partial positive charge. Such charge development, okay, on fluorine or hydrogen, okay, is going to create a dipole, okay. So I hope that explains the question number 85. Next, we have been asked in this question the correct order of basicity of the following amines. Now, here basicity is directly proportional to hybridization of nitrogen atom, and we should know that order of basicity will be sp3 greater than sp2 greater than sp. So higher the s character, less will be the basic character, okay. Higher the s character, less will be the basic character. So out here, if we judge the hybridization of all these nitrogen atoms, we will find that this is going to be sp3, this is your sp2, that too is your sp2, this one also is your sp2, okay. So obviously 4 will be the most basic out here, there is no doubt about it. Now we have to decide the order among 3, 2 and 1. Now out here, in the second point, we would like to mention that the basic character will be dependent on the availability of lone pair. Now what I mean by that is, if lone pair is involved in aromatization, as we can see in pyrrole or in case of indole, okay, this is your pyrrole, structure 1 is your pyrrole, structure 2 is your indole, okay. Then compound is less basic. That means we can say that 4 is the most basic out of 1, 2, 3 and 4. Okay, then it will be followed by 3, because the lone pair on pyridine is not involved in aromatization, okay. This lone pair is not involved in, this particular lone pair is not involved in not involved in aromatization. Why so? If you look at the structure of pyridine, what we will understand is this particular lone pair is in the sp2 hybridized orbital, whereas the pi electrons are getting delocalized within these p orbitals. Okay, and the angle between this p orbital and the sp2 over here is going to be 90 degree. So that is why this pyridine lone pair is not involved in aromatization, and hence pyridine is more basic than our pyrrole. However, in case of pyrrole, what we can see is this electron is involved in aromatization, and hence it is less available. Now, out of pyrrole and indole, which will be more basic? Obviously, it will be indole, because when pyrrole gets protonated, when the pyrrole gets protonated, all right, when the pyrrole gets protonated, from aromatic it becomes non-aromatic. Okay, so there is loss of aromaticity. However, when the indole this gets protonated, okay, this gets protonated, complete aromaticity is not lost. So aromaticity is partially lost for this ring. Okay, but aromaticity is not lost for the benzene ring. All right, for so that reason we will say 4 will be more basic than 3, and whereas we will say 2 is more basic than 1. Okay, and hence that way our answer is going to be A. I hope that clarifies the question number 86. Thanks for listening.